So last time, did I start that recording? I did, yeah. Well, so the assignment is due on the 8th, which is Monday after spring break. Next week is spring break, of course. And the exam on chapter 1, 2, 3 will follow after that. The exam questions are, things very much like the homework and, actual examples that I have done in class. So that's where all those questions are coming from. So things like this, like last time I asked you about, will you be checking your email if we have? Sure, yeah, absolutely. I'm available by email. Okay, so if you have questions, we can, I'll be able to answer them over email. If you want to meet over break, it's, some individual meetings, it's okay as well. I'll be around. Will we be able to use a note page on the exam? Well, I mean, since I take things from the notes, yeah, that'll be fine. You can use a page of notes for your exam, sure. Okay, so one piece of paper. So, one 8.5 by 11 paper, front and back of notes are allowed. Oh no, we'll just meet like this during class time, and then everybody will turn on their webcams and point the webcam at like their exam paper. So at their workspace, I guess, so I can just watch what they're doing, and that's it. Okay. Does everybody have a working webcam on their computer, attached to their computer, or does anybody not?
Yeah.
Okay. So you'll point the webcam at your workspace, and that'll be sufficient. Okay. Yeah. Unfortunately, math exams you can't do them online because it's not just it's not just written. I mean, yeah, it's written, but I mean, there's too much symbols used here. To do it on a lockdown browser or something like that. So this is just the easiest way to do it. And then you'll have time to scan your exam, and then you'll upload it to Dropbox just like the homework. Yeah, so well, I'll talk about that on Monday. Okay, but very similar to how we do the homework. All right. So last time I asked you to prove that the following is true. So why don't we start off with that? To prove that the following is true. So A intersection B is the empty set if and only if A intersection B complement is equal to A. And remember also, right, the double implication tautology is that P if and only if Q is logically equivalent to P implies Q and Q implies P. So logical equivalence is also called double implication for this reason. So you have to have two proofs for an if and only if proof, if you're using the double implication tautology, which typically you do. So here's a proof. All right, so this is P. A intersection B is equal to the empty set if and only if Q, A intersection B complement is equal to A. So first you have to prove, well, you can do them in either order. This direction, we'll do this direction first. Okay, and there's three ways to show an implication statement is true. Right? Direct proof, assume P, show Q. Contrapositive, assume Q naught, show P. Contradiction, assume P and Q naught, find the contradiction R and R naught. Of course, this is impossible, R and R naught, so your initial assumption must be false. All right. So let's do direct proof here. So assume that A intersection B is equal to the empty set. Okay, assume A intersection B is equal to the empty set. Now we need to show that A intersection B complement is equal to A. All right, so to show these two sets are equal, I will show that A intersection B complement is a subset of A, and that A is a subset of A intersection B complement. Okay, so show this subset containment and then show the other subset containment. All right, well, if X is an element of A intersection B complement, then by definition, what? Well,
X is in A and X is in B complement.
All right. So let's say it this way. Let X, because this is the way I've been saying to do it, be an element of A intersection B complement. So by definition, what you just said, X is in A and X is in B complement, right? But, that's all we need. So it's simply by definition. If X is in A intersection B complement, then, right, X is in A by definition. And that's it. The fact that X is also in B complement isn't really relevant here. So A is a subset of A intersection B complement. Right? So let X be an element of A. Now what? We want to show it's also in B complement. We want to show it's in the intersection of A and B complement. So how can we show it's in B complement? Well, let's use the assumption. Because A intersection B is equal to the empty set, right? And X is in A, and A and B don't overlap, where is X not?
In B.
X is not in B. In other words, X is not in B. In other words, X is not in B means X is in
B complement.
B complement. So X is in A and X is in B complement. Therefore, X is an element of A intersection B complement as required. Okay, are we done? Are we done with this if and only if proof? All right, what were we trying to do?
No.
All right, we're trying to prove this is true. A intersection B complement, or sorry, A intersection B is empty set if and only if A intersection B complement is equal to A. So far we assumed this is true, and we showed this is true. Now we need to do the proof in the other direction. All right, so you can do the proof either, by direct proof, contradiction, or contrapositive. Let's do it by contrapositive this time. So by way of contrapositive, we're trying to show that, if this is true, then that is true. All right, so if Q, then P. So instead, I will prove if P naught, then Q naught. Okay, so assume P is not true. That A intersection B is not the empty set. Assume that A intersection B is not the empty set, and then we're going to show that these two sets are not the same. All right, so this is by contrapositive. And we'll do it directly as well. So assume that A intersection B is not the empty set, meaning what? So if A intersection B is not the empty set, then what?
There is an X in both A and B.
Therefore, there is some X, an element of A intersection B, that is, X is an element of A, and X is an element of B. Because X is an element of B, where is X not? Because X is in
B complement.
it's not in B complement. Because X is in B, it's not in the things that are not in B. Right? Because X is not in B complement, we have that X is not an element of A intersection B complement. Right? So X is in A, but X is not in A intersection B complement. Therefore, what about those two sets? What can you tell me about those two sets? The set A, and the set A intersection B complement, where there is X in A, but not in A intersection B complement. So what about those two sets? Are they the same? Are they equal as sets?
No.
No, they're not the same. And that's what we wanted to show. Thus, A is not equal to A intersection B complement, as required. So that's a proof by contrapositive. I often like doing that with if and only if type things. Prove if P, then Q. If not P, then not Q. To me, that's, makes sense to me like that. You don't have to. It's just a personal style of mine. But let's do a direct proof now instead. Let's do a direct proof instead, right? So this was a contrapositive proof of that direction. So let's do this again. This time a direct proof. So we're trying to show, in this case, right, if A intersection B complement is equal to A, then A intersection B is the empty set. So assume that A intersection B complement is equal to A. Right, now we want to show that there are no elements. Well, actually, this is more a proof by contradiction. Yeah, this one is one of those things where it's kind of not doable so easily via direct proof. Well, no, we can do it. Let's do it direct. This one's okay, I think. Assume that A intersection B complement is equal to A. So if X is an element of A, then because A intersection B complement is equal to A, we must have what? If X is in A, then because A is equal to A intersection B complement, where must X also be?
In A intersection B complement.
Yeah. X is A intersection B complement, which implies that X is an element of B complement as well. So X is not in B. So if X is in A, X is not in B. If X is an element of A, then X is not in B. Therefore, let me write that sentence. You don't have to, but let me write it. So we have shown that any arbitrarily chosen X in A cannot also be in B. Thus, A intersection B is empty. So actually, the proof by contrapositive, I think, is a little clearer. All right, we assumed A intersection B is equal to the empty set. Now, if you take X in A, we found out that X is also in B complement, meaning that X is not in B. So, for any X in A, X is not in B, so A and B don't overlap. There is nothing that is in both A and B. It seemed to flow more naturally by assuming if there is something in A and B, right, then A intersection B complement is not the same as A. So I think the contrapositive proof was a little clearer, but anyway, there's both of them. All right. The assignment Assignment 3 due on Monday. And here it is. Is there any questions on it at this point?
Number 5.
Mm-hmm.
I was wondering if you could give us maybe a little starting point for that.
Well, if X is in A intersection B intersection C, then X is in B. All right, X is in A, and X is in B, and X is in C. Do you guys see my cursor or no? Can you see? You can see the highlight here, right?
There, yeah.
Yeah. All right, so two sets are disjoint. All right, so homework number 3. Problem 5. All right. So if X is an element of A intersection B intersection C, then necessarily X is in any one of those 3 sets. Right? It's in B. It's in A, and it's in B, and it's in C. Right? Then X is an element of A, and X is an element of B, and X is an element of C. Right? So in particular, X is in any one of the 3. B. A, say. Something like that. Right? If X is an element of A complement intersection B, intersection C complement, say, then X is an element of A complement, and X is an element of B, and X is an element of C. In particular, what? Compared to this, in particular, what? If you eat a banana split, right, then you're eating something that has bananas, ice cream, and whipped cream, right? So necessarily you're eating some banana. Right? A banana split is bananas and ice cream and toppings or whatever. Banana and ice cream and toppings. So necessarily you get some banana in there, forgetting about everything else. All right. So here my banana split has apples in it. Here my banana split has what?
Not apples.
Not apples in it. In particular, X is not in A.
Yeah.
Right. So these sets, right? So A intersection B intersection C and A complement intersection B intersection C are disjoint. What's disjoint mean? What's disjoint mean?
The intersection is empty.
The intersection is empty. So. The term disjoint is used a lot, so it's definitely a term you want to get used to. All right. So why are all these guys disjoint? All those sets there. I mean, there's 8 different sets. Why are they all pairwise disjoint? Why is any two of them disjoint? Right, so this set and this set are disjoint. Why? Because in this set, elements are in B. And in this set, elements are not in B. They're in B complement. And when you have an element of this set, it necessarily is in B. When you have an element of this set, it's necessarily not in B. It's necessarily in B complement. So they can't have any overlap. They must be disjoint. So what's the deal with all of these? For any two of these things here, they differ by what? Any two sets here, how do they differ? How do they differ, these sets, from each other?
By their complements.
Yeah, I mean, and you know, for all the ways of choosing 0, 1, 2, or 3 complements among the three sets, you know, this is all 8 of them. So any pair of these sets, they differ by complementation in at least one of A, B, and C, right? So like this one and this one, so the 7th and the 8th, right, they differ by complementation at A. The 4th, the 4th and the 8th, they differ by complementation at B. They also differ by complementation at A, but, you know, just one is enough. So they differ by complementation in one set, A, B, or C. So they can't overlap, because one of them is going to have elements of B. Another one's going to have elements that are not in B. So there's no overlap. Okay, so we need to say that clearly. So you need to think about how to say it. Okay? You need to think about how to say something like that. But the, you know, basic reasoning is like what I've written here. If X is in A intersection B intersection C, then X is in A and X is in B and X is in C. I mean, you don't have to write it like this. This is too much, what I wrote. You know, if X is in A intersection B intersection C, then X is in A. If X is an element of A complement intersection B intersection C complement, then X is in A complement. So I mean, you know, here's a better, so here's a shorter proof. So here's a better proof. Here's a more succinct proof. Is there two C's? Succinct? I don't have to look that up.
Yeah.
Okay. If X is in A and B and C, then X is in A. If X is an element of A intersection B intersection C, then X is not in A. Therefore, they're disjoint. That's all that needs said. That's all that really needs to be said. Actually, you know, I mean, nothing really needs to be said. All that needs to be said is they are disjoint. I mean, it depends who you're talking. Depends on your audience. I'm actually asking you to give me a proof, so you actually have to give me one. But you know, that's it right there. That's all that needs to be said. This is a little more long-winded. It's not wrong, but it's not as succinct as it should be.
Little mini proofs.
Yeah. You know, the idea in technical writing, in all technical writing, is, you know, be complete in your explanation, but be brief. And of course, these are competing goals, right? To be complete, you have to write more. But to be brief, you want to write less. So you want to, you know, say it all as briefly as possible. How can I give you an example of that? Well, there's lots of examples of that, but, you know, I mean, if you're ever in a situation where, you know, someone asks you, I mean, later on in life, you know, what is it that you do? You know, and you start telling them, you know, they don't want a big explanation. They want to know in one sentence what it is that you do. You know, and if what you do is like, you know, something a little bit, you know, out of the ordinary, I mean, if you say I'm a lawyer, fine, I'm a lawyer. Okay. I mean, everybody kind of knows what that is. Or I'm a corporate lawyer, or I'm a patent lawyer, or criminal attorney or something. You know, everyone sort of knows what you mean. But I mean, if you work at the base or something like that, you know, what do you do? Well, you know, I work on maintaining flight systems for F-22s. Or, you know, they want to know quickly what it is. You know, or if you're trying to get, you know, trying to get funding for your research grant or funding for your startup company, you know, funding agencies and investors, they want to know briefly what's going on, but they want to know everything too. So, you know, this is the type of writing skill that's very useful. Okay. Other questions about the assignment? We've got a lot of examples like number 4. And number 3 was just, you know, showing 2 sets are equal by showing one is a subset of the other in each way. The first is a subset of the second is a subset of the first. Okay, so I'm hoping we're getting up to speed on that. So please get started on it if you haven't already. You know, but we'll talk more about it on Monday. All right. So just to finish up our presentation here on sets. You know, we were you know, talking about Cartesian. We defined what a Cartesian product is. The Cartesian product of 2 sets, A and B, is A. We often say A cross B. So sometimes people call it the cross product, but it's the Cartesian product, A cross B. It's the set of all ordered pairs, little a, comma, little b, where A is in set A, little b is in set B. And this thing here is called an ordered pair, where with ordered pairs, order matters. With sets, order doesn't matter, right? So like the pair 3, -4 is different than the pair -4, 3. Whereas, you know, the set 3, -4 is the same as the set containing -4, 3. So 2 different ideas there. And then we started talking about infinite cardinality. So the basic infinite cardinality is this cardinality called infinitely countably infinite, or countable, or enumerable. So the set n of natural numbers, that's said to be countably infinite. So sometimes you might want to, instead of counting starting at 0, you might want to count starting at 1. You know, it's fine. So the positive integers, it's the same thing as countably infinite or enumerable. It's an infinite set, but you can list the things out. First element, second element, third element, fourth element, so on and so forth. So sets are countable when you can label them with the natural numbers. Right? When a set A has a 1-to-1 correspondence, or, you know, a labeling with the natural numbers, you call that set countable. So like the set of even natural numbers, 0, 2, 4, 6, 8, 10, dot, 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 to n, dot, 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 right? That's countable, right? Because you label 0 with 0, 1, 2 with 1, 4 with 2, 6 with 3, 8 with 4, 10 with 5, 2n gets labeled with n. So that e is countably infinite, just like the natural numbers. Even though e is a proper subset of the natural numbers, they have the same cardinality. With infinite cardinalities, things become, unusual. Things become counterintuitive in certain ways. The integers, the full set of integers, the positive integers, the negative integers, and 0. That's countably infinite as well, because you can label them with the natural numbers. 0 you label with 0, negative 1 with 1, 1 with 2. Negative 2 with 3, 2 with 4. Negative 3 with 5, 3 with 6. Negative 4 with 7, 4 with 8. In general, negative n is labeled with 2n minus 1, and n is labeled with 2n. So you've labeled all the integers, positives and negatives, with the natural numbers. All right, the 0th element, 1st element, 2nd element, 3rd element, 4th element, 5th element, 6th, 7th, 8th, so on and so forth. So z, the set of integers, even though it properly contains the set of natural numbers, they still have the same order, or same cardinality, countably infinite. All right, so here's the neat one. So the positive integers, Cartesian product of positive integers, or z plus cross z plus, is again countable. It's again countable, even though there's sort of not really an obvious way to label those guys. But this is the way it goes. Okay, you write out the whole set as such, as a two-dimensional array like this. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 7, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, so on and so forth. And you label them like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. This one is going to be 28. And these numbers here are known as the triangular numbers. It's the number of items in a triangular stack. Right? Triangular stack of one thing, there's one element. A triangular stack with that many rows. Right? So a triangular stack of 2 rows has 3 things in it. 3 rows has 6 things. Of 4 rows has 10. So like this, that's like a rack of pins at the bowling alley. Right? It's 10 pins in a 4-row triangular stack. And if you've ever played 8-ball or straight pool, right? I mean, a full rack of balls on a billiard set is a triangular stack 5 rows deep, and that's got 15 things in it. And these are the triangular numbers. And then this triangular number right here, 28, right? That's the number of dominoes in a set of double 6 dominoes. If you've ever played dominoes, it's a triangular stack of dominoes 7 rows deep. So in general, the triangular number, right, so this is T7, which is equal to 7 times 8 over 2. In general, the triangular number is n, the nth triangular number is n times n plus 1 over 2. So like for the bowling pins, 10, right? It's 4 times 5 over 2, it's 10. 5 times 6 over 2, 15. So on and so forth. So every number down here, so this is the triangular number for n minus 1 plus 1. So triangular number for n minus 1 plus 1. So you can enumerate all of z plus cross z plus, positive integers cross positive integers. Right, so we have, this is the one-to-one correspondence between n, we left out the 0, leaving out 0, which is fine, and z plus cross z plus. So z plus cross z plus is countably infinite. Which set does this imply is also countably infinite? It's a subset of z plus, well, sort of a subset of z plus cross z plus. Which common set of numbers? Which common set of numbers are built up from pairs of integers? So other than the integers themselves, which set of numbers is built up from pairs of integers? Which set of numbers is built up from pairs of integers? Come on, guys. Hello.
The XY plane.
Right, but those are not numbers themselves. Which numbers are built from pairs of pairs of integers?
The reals.
That one is actually not built up from pairs of integers. That's the first not countably infinite set. The rational numbers. So Q, which is equal to the set of all A over B, such that A is an integer and B is an integer, and B is not equal to 0, is also countably infinite. So even though the rational numbers, so we'll just show the positive ones. The positive rationals are countably infinite, and then you can just do alternating, positive, negative to get the full set. So here is the labeling just for the positive ones. Or just the positive ones. So there's 1 over 1. Oops, 1 over 1. 1 over 2. 1 over 3. 1 over 4. 1 fifth. 1 sixth. 1 seventh. 1 eighth. So on and so forth. 2 over 1. 2 over 2. 2 over 3. 2 over 4. 2 over 5. 2 over 6. 2 over 7. 2 over 8. 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, 4, So you do the same thing that you did before. But of course, you know, these guys, they repeat themselves, right? But anytime you come up against a repetition, you just throw it out. All right, so here's number 1. Here's number 2. Here's number 3. Here's number 4. Here's number 5. We already got that one. Just leave it out. Here's number 6. Here's number 7. Here's number 8, 3/2. Here's number 9, 2/3. Oops. Here's number 10, 1/4. 5 over 1, that's number 11. 4 over 2, it's the same as 2, so just leave it out. 3 over 3, it's the same as 1, just leave it out. 2 over 4, it's the same as a half, just leave it out. And then what am I on? 12, number 12. Essentially, you know, the fraction needs to be in lowest terms. So anytime a fraction is not in lowest terms, you just chuck it out, right? So 2/6 is the same as 1/3. 2/8 is the same as 1/4. The ones over 3 are all in lowest terms, of course. That's not 4 over 6, 4 over 8. The ones over 5, or the ones with 5 on the top are all in lowest terms. So 12, so this is going to be 6 over 1. So that's 13. 14, 15, 16, 17, 18, so on and so forth. So the rational numbers are countable. Right? So, of course, we leave out A over B when it is not in lowest terms. Because it would have been counted earlier. But the first example of a set that is not countably infinite is the real numbers. The real numbers themselves, however, are not. So let's give a proof of that. And this proof is due to Georg Cantor. It is known as Cantor's diagonalization argument. So R is not countably infinite. It's too big. So again, with infinity, weird things, you know, start happening. And R is simply too big to be countable. All right, we'll show that, you know, the set of all x such that, so that the interval from 0 to 1, 0 is less than x is less than 1 is too big to be countable. So this is a proof by contradiction. It's not an implication proof by contradiction. It's just a simple statement proof by contradiction. So we want to show that R is not countable. So by way of contradiction, assume R is countable. So by way of contradiction, assume the negation. That is R, the interval from 0 to 1 is countably infinite. Okay, each element x in 0, 1 in the interval from 0 to 1 is expressed uniquely as uniquely in decimal form, as long as what? Does anyone know? An infinite string of 9s repeating. All right, so you can express every element, and every real number as a string of decimal, as a decimal in its decimal form, right? In its base 10 form. So 3.14159, blah 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 blah, right? Or 1/3 is 0.33333, or E is 2.71 something something something, right? I mean, all these numbers, they have a unique decimal string, as long as you don't use repeating 9s. Repeating 9s ruins the uniqueness. Does everybody know that? Like 1 is actually equal to 0.99999. Repeating. That's why. That's the only non-uniqueness that happens. 1 is actually equal to this. Did you guys all aware of that? Is anyone not aware of that? Right. If you let x equal 0.9999 repeating, then 10x is equal to 9.999 repeating. Right. So 10x minus x is equal to what? Is 9. So 9x equals 9, so x equals 1. Right? So you let x equal to be 0.99999, and then you actually get that x is equal to 1. So decimal expansions, they give you unique representations of real numbers, except for, the 0.99999 business. So you just leave that out. All right? So here is our hypothetical. Enumeration, i.e. labeling, of the interval from 0 to 1. Right, so the first number, right, it's going to be something. The second number going to be something. Third number going to be something. Fourth number is going to be something. Fifth number is going to be something. Sixth number is going to be something. So on and so on and so forth. So how do we write out the first number? Well, it's going to be something. 0.131456177989999312213. So I mean, it's something. 0.989898987654 something something. 0.111121200000. Ending off with zeros is fine. 0.3103101295. 0.1121333888. So on and so forth. 0.1573121578665 so on and so forth. Okay. Look at the first decimal place here. The second decimal place here. Third decimal place here. Fourth decimal place here. Fifth here. Sixth here. Construct a decimal expansion that is different than 1, different than 8 in the second spot, different than 1 in the third spot, different than 3 in the 4th spot, different than 3 in the 5th spot, different than 2 in the 6th spot. Right? So now, to find x equal to D1, D2, D3, D4, where Di is not equal to the ith digit of number I. Therefore, x is in 0, 1, but not equal to any other number in 0, 1. A contradiction. Because we were supposed to have enumerated all of them. In our list for 0, 1, in our enumeration for 0, 1. Of 0, 1, a contradiction. Right? I mean, you've got some purported enumeration, but now you just make a number where it's different than 1 in the 1st spot, different than 8 in the 2nd spot, different from 1 in the 3rd, different from 3 here, different from 3 here, different from 2 here. So this number that you made is not equal to any of these labeled numbers here. But the labeled numbers were supposed to be the whole thing. But it's not, because you missed one. So it's not countable. The initial assumption that it was countable can't be right, because we had achieved a contradiction. Okay, so everybody have a good spring break, and I'll see you on Monday. You got any concerns, questions, just email me, okay? I'll be checking my email over spring break. I'm not going anywhere, obviously. Okay? All right, guys, enjoy. We'll see you afterwards.